So this is Matt. He's been with us before at PasswordCon here in Las Vegas. And like 20 minutes ago, he told us that he only pulls the doctor card when he's mad at somebody. But Matt actually has a PhD in password cracking and optimizing how he can crack your passwords. So and he told me, he put actually out on Twitter that he was going to try to make this a little less academic. And I can only say thank you for that. And I look forward to talk, Matt. Go ahead.
Thank you very much, Per. So I got my start, as he mentioned, basically when I decided to go back to college. And I was very lucky to be able to get involved with the E-Crimes Investigative Technologies Lab at Florida State University. And the whole idea behind that lab is to do research and develop better forensics tools for law enforcement. And as you can imagine, cracking passwords definitely kind of falls under that category there. So that was a tremendous opportunity. I've since graduated, found myself a real job, and so since I like that real job and I want to keep it, I really need to mention that all the password cracking and password security research that I'm doing is on my own time, and so all these opinions are my own and not my employer's. So I was spending a lot of time trying to think about what I should submit here to PasswordCon, what would be fun. And I just wanted to mention a couple of other little hobbies that I'm doing right now when it comes to password security. One thing is that IBM right now is offering a real-life quantum computer free for any researcher that wants to use it. So you can log right onto this here. It's a 5-qubit computer, so it's a real one. It's not like those D-Wave ones where it's somewhat kind of like quantum computers. And it's basically like the old mainframe days where you write up your program, you submit it to them, it gets queued, eventually they run it, and then they send you the results back for it. And it's just a tremendous, wonderful opportunity. Now, quantum computers have the potential to really impact the password security landscape. I won't really talk about that because there's been other conference talks that people have mentioned about it. But what I really wanted to highlight once again, though, was that this is free and this is something that anybody can do. So I highly recommend that everyone here in this audience go out, sign up, and then just play around with this here a little bit. Even if you don't care about quantum computers, just do it for the bragging rights. Have it up on your screen on your work. When your coworker comes by, you can be like, and they ask you, like, what are you doing? They're like, oh, I'm just programming a quantum computer. What are you doing? I mean, are you still using a classical computer? That's, really lame. So, I mean, that's just kind of what I want to really kind of highlight about that.
Yeah, but that's when your coworker then reminds you that they're a PhD.
So another, research topic that I'm very interested in right now is trying to figure out what a hashing algorithm for biometric measurements should look like. Because this is a really big problem right now. And I'm not talking just about your iPhone logging into that or potentially logging into a website with your fingerprint. I'm talking about these large databases of biometric information that's currently out there right now. I mean, for example, who here had their fingerprint stolen from an OPM hack at all? I knew I'd catch a couple of feds that way. But it sucks, doesn't it? I mean, and the problem with biometric information is once it's stolen, it's gone, okay? There's no getting that back. You can't change it. It's just gone. So this is an area that we really need to have better research on in order to try to limit the value that these biometric databases provide to an attacker. So that's all cool stuff, but I'm going to talk to you about modeling instead. I know this is generally not something that people really, get super excited about. Like, oh, hey, we get to use, different types of, regular grammars and go ahead and try to figure out how to go ahead and model how people, behave. But it's something that I feel is very useful for probably just about everyone here in this room. Because there's definitely offensive, uses for this here when it comes to, developing better password cracking algorithms. Because if you can model someone and how they create passwords, you can definitely, weaponize that model in order to, crack their passwords better. But there's also lots of defensive applications as well. So you can start talking about how you make better, password security policies, and how, there's a couple other applications as well. So regardless of whether you're on the offensive side or the defensive side, or you just want to do some more research, there's a lot of stuff here that that I hope can be useful for you. So it can be very easily said, though, that we don't need better modeling techniques. I mean, current attack techniques are amazingly good right now as it is. This was based upon the more recent MySpace leak, and Cynosure Prime posted basically a write-up of how they were attacking it. And they managed to achieve a 99% success rate against all these MySpace users. I mean, that's really good. I mean, whenever you can say that you cracked 355 million passwords, you don't need to up your game. Your game's already up there, okay? You don't need to really advance your techniques that much. But there still is a lot of room for improvement in areas where that improvement is really kind of needed. So, I mean, for example, when we talk about computer forensics, hashes are getting stronger. You can only, especially when you're talking about like full hard drive encryption or other types of file encryption, you're really kind of limited in the number of guesses that you can make. Or you start, people actually start deploying Argon 2 eventually, maybe. On the defensive sides, we really want to go ahead and have these better models so we can tell what's a strong password versus what's a weak password, so we can make more sane password policies. And then also I'll talk about honeywords, which is a way to be able to make basically fake passwords in order to mess with people. But what it really comes down to is that we have all these different data sets that are getting released and that we're cracking and we're learning about. And a lot of times, we'll go ahead, we'll run some statistics against them. We'll make some great, graphs. Per and Jeremy made this one here about the LinkedIn list. And there's a lot of little cool tidbits in there and a lot of kind of useful information. But kind of the question comes back to, how are we going to actually make use of this information? How can we go ahead and use this to improve our password cracking techniques or improve our defensive techniques in order to make people more secure? So that's what I was really kind of curious about, is how can we go ahead and kind of automate the learning process of, here we have this leak, and how do we, incorporate that into our knowledge of how people create passwords. So when I first really kind of started working on this research, my approach was I wanted to make an automated rule generator. So I wanted to go ahead, parse a list of, cracked passwords, and then just create mangling rules based upon that list in order to feed into, John Ripper. Hashcat wasn't really around that time, but that's the kind of general approach that I wanted to take. And I ran into a lot of different problems, which I'm going to talk about really shortly here. But it's a very useful technique. So, I mean, if you're looking for tools that do this type of thing, I would probably highly recommend either Barbell's Rule Finder or Password Analysis and Cracking Kit, PAC. The problem is both of those tools haven't really been updated in the last couple of years. So if you're looking for a research project and Per hasn't already tasked you with something, I would say that this is probably an area where there definitely can be a lot more work being done. Probably, though, the one area that was the biggest problem when I was running into when trying to go ahead and create an automatic rule generating kit was that the words that people use in passwords have very different probabilities associated with them. A whole lot of people use password. Some people use monkey, and then or baseball, and then you have people that are down there who are using like piano or zebra, and you really kind of want to be able to represent that. And it's hard to do in a lot of your password cracking sessions that you run. So for example, if you want to use like the entire core logic rule set that they released there, you have to run a really small dictionary against it if you ever wanted to have it complete. So a lot of times in order to crack passwords, I'll have a very targeted input dictionary that I'll run really advanced rules against. And I'll have a much larger input dictionary that I'll run much more targeted rules against in order to try to do that. But that's it's a big pain in the butt. I would like to be able to just go ahead and run my cracker and have it be able to take into account the different probabilities of these different words. So that way I do a lot of advanced mangling rules automatically with these really very common passwords, and then less mangling rules with the less common passwords. Also, combining different mangling rules is kind of tough, especially when you're talking about learning from a data set. So doing a very basic idea of like, okay, people put digits at the end or they, capitalize the first letter is pretty straightforward. But when you start combining it, so like, okay, they capitalize the second letter in the word and they replace the A with an @ symbol, and now they add digits to the end and then they have a special character. That's really hard to go ahead and figure out how to combine those different rules together. And when you start to do that too, the number of rules that you have just absolutely explodes, where all of a sudden you're generating millions, if not billions of rules. And I'm not exaggerating here. That's actually what's going to happen when you start trying to go ahead and do this types of modeling. Also, when you do a lot of this training, it's often not very predictive. So you might not see something exactly in your training set, but you'd want to try that in your cracking session. So you want to be able to support that. Now with some of these bigger data sets, that's not as much of a problem. I mean, when you have 360 million passwords, you're probably going to see just about everything. Or if you don't see it, then you generally don't care about it that much. But when you're trying to make a more targeted rule set against, let's say, a corporate entity, you might only have, several thousand passwords. And you want to be able to learn based upon that there. And so that's what really kind of drew me to probabilistic context-free grammars. Because when we talk about how people create passwords, we generally always talk about probabilities. So we say, okay, 90% of people, capitalize the first layer of their password, or 80% people put digits at the end, or 5% of people use their dog's name in their password. And so these are all probabilities. So it'd be really nice if we could take all these probabilities that we're talking about, the probabilities that we learn from these different data dumps, and directly incorporate them into a model and then generate password guesses based upon those probabilities. So that way we don't actually have to manually create all these different rules. We just kind of let the probabilities kind of sort it out for themselves. And, oh, sorry, yep. Oh, yep. That was definitely a good kitten there. And that's pretty much my cat's. Oh, it is kitten?
Twice.
Kitty?
No, the H instead of the N.
Oh, that's intentional there.
I know,
Yep.
but we don't get it. Sorry.
Oh, it's kind of a lolcat speak, where they'll go intentionally make it the cat speak incorrectly and not use proper grammar, which I'll admit it's probably a little ironic since I'm talking about grammar here and proper grammars.
Irony's good.
Yep. So I can start talking about all this and how probabilistic context-free grammars are good. But really, I mean, the proof is that when our researchers have done studies on this, is that probabilistic context-free grammars, when you use them, generally tend to mimic how people create passwords better than alternate methods. So this was done by Carnegie Mellon University last year when they were going ahead and testing different password cracking attacks, and they have basically a password guessability lab that you can submit passwords to and have them running these attacks against it. And probabilistic context-free grammars really kind of did better than just about everything else. And that includes, let's say, the pros, which was the core logic team was brought in, and they definitely know a lot about passwords. And while they eventually were able to crack more passwords, if you really want to talk about just how it accurately modeled the precision of the grammar, PCFGs pretty much did better than anything else. So that's kind of my spiel on why this probably is going to be interesting to you guys, hopefully. So I'm going to have to do a little bit of academic stuff here, and I apologize. But what I really wanted to do was just talk a little bit about what probabilistic context-free grammars are, because there's a lot of misconceptions. And probably the biggest misconception is that they're complicated and require lots of math. It's kind of great when I get up and talk about people and they're like, oh, he's talking about probabilistic context-free grammars, he must be smart. Not true. Well, hopefully it's true, but it doesn't automatically flow from that there. Probabilistic context-free grammars are actually probably easier to use than Markov models there. I mean, there's really no math required when we talk about context-free grammars themselves. It's more like Mad Libs. So any type of grammar can be defined by 4 different things. Non-terminals, which can be replaced, and they're basically variables. Terminals, which are kind of the constants, they can't be changed. Replacement mapping variables to the constants. And basically your start variable that you start out with. And what you do with a context-free grammar is you start with your start variable, and like Mad Libs, you just start replacing it until everything that you have is now a constant. So let me go over an example of that there. Let's start with this very basic kind of context-free grammar that's kind of modeled after passwords here. And you have a start variable s that goes to letters and digits. And you have an L that goes to 3 different words here, and then D that goes to 3 different digits. So with the context-free grammar, you start with your start variable here. And then you just go ahead and replace it. So you replace that with L and D. Now, since it's context-free, each of these different variables here, these are 2 different variables, can be replaced independently of each other. So if I want to, I can go ahead and replace that L with anything. So for example, I can replace it with baseball. And then I take that D and I replace that with 82. And since everything now is a constant, I can't replace it anymore. Now I have my final terminal. So as I said, it really is just kind of like Mad Libs. You just keep on doing this. And while you can get more complicated with your grammar itself, essentially all you're doing is just this right here. And that's context-free grammars. Now, when we talk about probabilistic context-free grammars, unfortunately there's a little bit of math involved. But really, that's the only math that you do is multiplication. Nothing more complicated than that whatsoever. There's no calculus or anything else. You're not doing matrix multiplications or anything. It's just standard multiplication. And what you do is that every single replacement that you have has an associated probability with it. So that the final probability of your terminal is the product of every single replacement it took in order to get to that terminal there. So just kind of going through that previous grammar that we had there, you start with your start symbol, and probability of that's 100%, because that's where you always start. And this grammar here, there's only one replacement, so the probability of the next replacement there is still 100%. We want to go ahead and replace the L with baseball. The probability of that's 10%, so 10% times 100% is 10% for this current running probability that we have. We replace the D with 82, which is a probability of 25%. And 25% times 10% is now 2.5%. And what this means is that the probability of this grammar generating the string baseball 82 is 2.5%. And this is incredibly powerful. So if you're cracking passwords, it's pretty obvious to see how you'd use this probability. You want to start with the most probable password guess, try the second most probable one, then try the third most probable one, and so on. Or if you're trying to go ahead and do it a little bit faster and parallelize it, you can take some shortcuts and instead say, I want to go ahead and generate every single password guess that falls above a certain probability threshold. So that way you can kind of limit the key space that you're searching against while still making use of this grammar. It can be used also for like password policies for defensive purposes, where you basically go and tell someone, hey, I'm sorry, your password's probability is just way too high. Because you actually have a probability associated with that password that they just created. And what's more, you can go ahead and suggest other alternate replacements according to your grammar that would reduce the probability of their password down to an acceptable level. So that way people can go ahead and create passwords kind of the way that they want, or at least somewhat related to the way that they want, while still meeting your security requirements. Yep?
Why wouldn't it factor in that certain digits may correlate differently with the words, the letters?
Okay, so that's a good question. Yeah, so I'll go ahead and do that. So the question was, how does this go ahead and correlate, let's say, the probability that certain digits might occur with certain words in a higher different probability? And the short answer is, at least if it's using context-free grammars, it doesn't. And the reason why I chose context-free grammars versus context-sensitive grammars is mostly because the training is much easier. And when it comes to passwords, I found that there's very few context-sensitive letter replacements. People, they might choose their dog's name, but then they don't choose, 82 related directly to their dog for the most part. It might occur some occasionally with, let's say, your daughter's name and then her birthday or something like that. So there might be some context sensitive, but that's really hard to model, unfortunately. And I'll actually talk about how you can cheat a little bit and get some context sensitive information and kind of mash it into a context-free grammar. So that's something that I've struggled with, but long story short is that most passwords I've found anyway, you don't have those context-sensitive replacements there. So and then the other thing I'll talk about a little bit is just honey words, which, as I said, are ways to be able to create fake passwords that look real. So that's kind of the end of the academic side of things. I want to talk more about the practical things, because I promised I'd do that. So this has been around for a while. And about last year, I decided I wanted to go ahead and completely recode my entire probabilistic context-free grammar. And part of the reasoning behind that was that it was becoming very hard to modify. I had basically baked in a particular type of grammar in order to model how people create passwords. And that was limited, and I wanted to make changes to it. And what was actually really driving that was I was trying to get into passphrase modeling with context-free grammars. So I was scraping Per's Twitter account and his blog posts and stuff like that in order to try to make a paraphrase generator. Yeah, I mean, so actually some of that's still going to get to GitHub results there. But basically I was breaking my code left and right, and I was getting really annoyed by it. And so I really wanted to do was kind of go back and be able to make a kind of a cracker that would be able to work with any generic context-free grammar. And what this means is I could really focus my time on trying to mess around with the modeling of how people create passwords. And I just have a tool that would just kind of work in order to be able to test and see how effective those models were when cracking people's passwords. So it's coded in Python, so that way it'll go ahead and run pretty much wherever you want it to go. It works with both John the Ripper and Hashcat. It is open source, so you can go ahead and grab it and modify it to your heart's content. And there's a lot of documentation that I've been trying to put up there on the wiki itself. And so kind of going back to why was I doing this, there's a lot of improvements in the grammars that I'm going to be talking about. So beyond from what I was doing before, another group at Florida State University decided to go ahead and modify the grammar a bit. And they had absolutely huge improvements in the results of just going ahead and changing how the grammar was laid out. And I think there's a lot more room for improvement even beyond this here. So what I really want to be able to do is allow other people to go through and kind of make their own grammars, make their own training programs, and then have the tool for them to be able to go ahead and test to see how well they work. So I include one kind of default training program in the GitHub page right now. I'm probably going to release a couple more as they mature a bit. But basically what you do is you run it on your list of cracked passwords. And it'll go ahead and generate a grammar for you automatically. The one thing that I really recommend is that you install the character detect Python package when you do this. It's not required. It'll give you a warning, but most people will probably ignore it. But as we learned from last year's Core Logic Crack Me If You Can competition, dealing with different encodings in your training set is a real pain in the butt. So I found this Python package actually handles a lot of that for you automatically, which is really nice. Because we got to show some love to some non-English speakers out there too. So I don't expect you all to read this, but basically when you run this here, it goes ahead and creates a config file that describes the grammar that you have. So you'll start with your start symbol up here. You'll have different replacement values in there, and it'll actually say, okay, your 8-character letters are stored in this directory. And this just kind of goes back to the fact that you can now modify your training program to run a completely different types of grammars, and then the cracker will automatically read this in and dynamically use this. So that way you can use the same password cracker or the guess generation tool for, let's say, passphrases versus password cracking. So now I'm going to talk a little bit about the basic model that I'm using right now in order to model how people create passwords. And what I expect when I go through this is good questions like the one over there, where basically you kind of ask you like, wait, there's got to be a better way to do this. That seems kind of ad hoc or crazy. There's totally a better way in order to represent something, and that's what I kind of want because that way, quite honestly, there is. I mean, every single choice I made here. I mean, there's a couple of alternate choices I could have made. So I really want people to go out and kind of make their own training program, make their own grammars, and then make a better model than what I have. So right now what I do is I first kind of go ahead and scan the password, and I break it up into what I call a base structure. And this is kind of resembles like a hashcat mask, where you go ahead and you break everything up. So okay, it's alpha characters, digits, or other. And I associate a number after as well. So this is like a 3-letter word or a 4-digit number. And the reason why I associate those numbers directly after it is so that way I can do things like I can represent 2 words, 2 4-character words versus 1 8-character word in my base structure there. So for example, cat123 would be parsed as an A3D3, or hashtag password16 would be parsed as a O1A9D2. So the next question, though, is, what about capitalization? Because, every once in a while someone capitalizes their password if they don't have to. So what you can do is have a replacement go to another replacement. So basically you can have a rule that your alpha characters go to essentially a capitalization mask that gets applied to your password as well. And those capitalization masks have a probability associated with them too. So that way, your A3 can go to, let's say, uppercase the first character at 10% of the time. And then that will go to, let's say, cat, a capitalized cat, at 80% of the time. Now you can get even further into that there as well. So now we can assign probabilities to individual words. And this is kind of really powerful. So that way we can say exactly, this is how probable, the word password is. And this is how often we want to use it in our, test set as well. And what's cool about context-free grammar versus some other techniques is like Markov models is that you can dynamically change this without going ahead and having to retrain your entire data set. So let's say I go ahead and I train this on like RawQ. I can go back later on and say, okay, I'm attacking, some other data set. So I'm going to go ahead and change the probabilities with these words and make these other words associated with that data set be really high. So that way we can start directly using things like your target's pet's name or the name of their site that they go to and so on. And we can do the same thing for digits as well. So that way you can raise the digits their birthday or their zip code to be much higher than you would normally see from your training set. So the next kind of improvement I've been making is modeling keyboard walks, because those are really popular, especially in your corporate environments. Because, if you're giving these people these crazy pass requirements, that's obviously what they're going to do. It's much easier to remember a keyboard walk than have to remember, some random passphrase. So I added a new non-terminal to the base structure K just to represent, keyboard walks that you have. So now we have alpha characters, digit characters, keyboard walks, and other. So for example, one QAZ pass would be a K4 A4. Or you could have multiple keyboard walks, so you have multiple K4s back to back there. Because that kind of represents how people kind of have a tendency to kind of do a keyboard walk here, and a keyboard walk over here sometimes. Now, one cool thing about this is in the training set, it basically creates a dictionary of all the different keyboard walks it finds. So if you want to, you can go ahead and rip this data out of the grammar here and use it for whatever input dictionary that you want for your normal password cracking attacks as well. So you don't actually have to use a context-free grammar when you're making use of this data. And there's not a whole lot of good keyboard walk data sets out there. So this makes a pretty easy way to do it. Now, one thing I want to kind of point out, though, is that you have to be really careful in training this. Because there's a lot of words out there that look like keyboard walks that aren't. And you don't really realize that until you start running this. And you're like, why the heck is Drew like one of the most popular keyboard walks? Well, it's a name. But, if you look at your keyboard, it's going to be, it's a keyboard walk as well. So you do have to kind of start adding some whitelisting on that. One other thing that I've been kind of dealing with that causes a lot of false positives is I was trying to include hitting the same key multiple times as part of a keyboard walk. I don't know how much people actually do that. I've been looking through the data sets. It's not really that common, it seems like. So I have to admit, in my training, I'm probably going to just go ahead and exclude that so I don't cause a keyboard walk like tree, which once again is, looks like a keyboard walk to the algorithm there. So, as was mentioned earlier, while rare, there occasionally are context-sensitive replacements as well. And you kind of want to, kind of shoehorn those into your cracking session. So, probably the most common examples of that are emoticons. So you don't want the, funny, smiley face to be parsed as, a A5, S1, A1, where it's, a word, special character, and then another word. Also things like, number one. That's a very common, context-sensitive replacement, and you want to be able to kind of model that. So what I did was I really cheated. That's what it comes down to. And I created a new class that says, okay, these here are, context sensitive. I'm going to go ahead and manually enter those in my training data set. And I'm just going to treat those like a whole other replacement, just add them together there. So that's pretty limited right now. As I said, there's not a whole lot of context sensitive data I've been seeing in the training sets. But if you want to extend that, you can start adding all sorts of emoticons there if you really want to. So letter replacements, this is actually something that I'm working on still right now. It's proved to be a little bit trickier than I originally expected. But one way to be able to handle this is to just handle it as another mask for your replacements, just like we do with capitalization. So that way your three-letter word goes to your capitalization mask, then that goes to your word, cat, and then that goes to potentially a replacement at a certain probability of, like, let's say replacing the A with an at symbol. Unfortunately, this does complicate the grammar quite a bit by adding another level into that there. But what's really kind of I'm struggling with is just training is difficult for this. Because you have to have a way to be able to differentiate that, cat one hat is not a replacement. It's just adding a digit right in the middle of that there. And then you can have words that have multiple replacements as well, like, password with the at symbol and the zero. So, I mean, that's still something to really kind of work on there. Luckily, not a whole lot of people still use replacements. I mean, it shows up if you're really trying to crack passwords, but it doesn't hurt the grammar not to have them that much. But really, I just want to be able to model this because that is something that's does occur. So that's the current grammar. So if you go ahead and you download it right now, you run it, that's kind of the grammar that's using in the back end. But I wanted to take just a couple of minutes to talk about potential grammars that I've been thinking about and eventually might get off my butt and start trying to code, because I think there are much better ways that we can go about doing this. So what I'd really like to do, though, is kind of go back and take a step back, get rid of those base structures, and really start to have a grammar that kind of models the thought process that people use when they're creating a password. Because people don't immediately create a mask and start filling it out when they create a password. They basically, you say you want to create a password, and they immediately go to kind of a coping technique in order to create that password there. They say, okay, I want to go ahead and create a dictionary-based password. So name of my dog, or I want to go ahead and create a passphrase, or I want to go ahead and use a keyboard walk, or you can get things like I'm going to go ahead and use my email address. So that can be the very first kind of step in your context-free grammar here, is figuring out which attack method you really want to model. Next, after that, let's say they choose a dictionary word based attack. So the next replacement would be, do you want to go ahead and choose a word from your input dictionary, or do you want to kind of dynamically generate a word from, let's say, a Markov model? Because I'm going to talk about this in a little bit, but probably the biggest weakness in current context-free grammars is that they're really dictionary-based. They're really dictionary-focused. And our input dictionaries really suck. So that's when you start seeing how Markov modes and neural networks start really being much more effective over a longer cracking session in context-free grammars. The reason for that is that your input dictionary has basically exhausted all the words that it could possibly crack. So when I start looking at the words that I didn't crack, a lot of them are really basic mangling techniques. It's just that I didn't have that word in my input dictionary. So you need to be able to have a way to go ahead and kind of dynamically generate those, because trying to keep an input dictionary up to date with all the new Pokemon characters is just a losing proposition there. But let's say you choose a word from your input dictionary. The next step in your context-free grammar there might be go ahead and apply required digits. So then you can have a probability of it appending the digits to the end, inserting the digits to the front, or performing a letter replacement. And you can have other different types of replacements as well. So at the same time, you'd be going ahead and applying required special characters if need be, or checking for length requirements as well. Now, for some of you formal grammar fans out there, you might be looking at this and saying, this looks a lot like a finite state machine. Okay, I know there's probably like one of you. But the answer is yes. And so one nice thing about context-free grammar is you can model finite state machines with it. So this way we can go ahead and start testing out how effective this is. And then if this turns out to be a really effective way to be able to go ahead and model people's passwords, we can go ahead and then go back and make a much more simplified model using a finite state machine. So that way we can go ahead and potentially make it faster or make it smaller. Actually, I covered this part here. But so as I said, one of the biggest problems, though, with context-free grammars is the fact that they are, are dictionary-based. Probably the best example, though, of a context-free grammar that handles brute force really well is actually the Prince attack in Hashcan John the Ripper. And what this does is it just takes an input dictionary and it starts combining all the words in an input dictionary together. And where it performs essentially a brute force attack is that if you have one character words in your input dictionary, it's going to start combining one character words together, and it essentially does a very basic brute force style attack, while at the same time adding digits to the end of your longer words. And so that's one approach, but I think that we can probably do better and start using some of these more advanced Markov modes as well to make just this a little bit more precise. So that's definitely on my to-do list. So I'd mentioned earlier passphrases. So this is kind of one of those big problems there. And one question I had was, can I go ahead and use a context-free grammar to kind of dynamically generate passphrases for use in password modeling? And probably the best example of a context-free grammar generating passphrases is SciGen, which is Omeg's CS paper generator, which is hilarious, by the way. Basically, some researchers coded this up and started making fake scientific papers, made them to conferences to see whether they could accept it. Might try that sometime with PasswordsCon here. The Nmap one, if you've ever read that one, it's hilarious. I probably won't talk too much about it because it's not safe for work, but it's a very good example of that there. So I thought there might be some potential there for that. So as I said, I started going ahead and trying to model this. And one problem I ran into was that you're just kind of your generic model of taking like a proper noun, verb, adverbs, and noun. Even when applying some probabilities to that, it would create too large of a search space. It just wasn't very effective at all. So a successful grammar probably needs more context-sensitive information than a pure context-free grammar you can get. But as I said, one way that you can start getting more information is really just target this against a particular individual. So not just going ahead and saying, I want to go ahead and generate passphrases for everybody, but I want to go ahead and base these passphrases on one particular writers. So one thing I highly recommend, and I have a little bit of code there in my GitHub repository, it's kind of iffy state, is to use what's called the Natural Language Toolkit, which is a Python library that you can run a corpus of data through, and it'll automatically go ahead and parse it down as noun, verbs, or adverbs, and break this up into different structures. So that way you can kind of use this in your training set. One thing I really want to try, though, is a much newer toolkit, is Google's new Parsey McParseface. I'll admit 90% of that's just due to the name of that tool. But basically, they released it as part of their TensorFlow toolkit, and it does a lot of the same types of things of parsing an input dictionary and breaking it up into these different types of grammar structures. So kind of the next question, though, is, okay, so we have this great and wonderful grammar. We spent all this time training it. We spent a lot of time trying to figure out how it works. How do we actually make use of this grammar? Okay, how do we get from the academic side back to more of the practical? So I'm going to start with the defensive applications first because I really want to kind of push those. But one way, and it's been really kind of fun, is with honeywords. So honeywords are kind of a synthetic password. So you kind of algorithmically generate these passwords, and you can use these for different types of opportunities. So they were originally thought of as kind of being like a canary type of alert sensor for your data sets. So you create these fake honeywords, and then if you ever see someone try to log in with those honeywords, then you know you've been pwned. So you can set that as kind of an alert. I have a little bit of disagreements on how it was kind of laid out in the original papers that talked about it, but one really cool tool I saw out there was this one right here that basically goes ahead and installs a client on people's computers and installs basically a fake account or a password into the computer's memory. And this password is unique to that computer. So it's a valid password, and you could use it to log in. It shows up in memory. If you have, you logged into it with Metasploit and you jump to credentials, it's going to look pretty much normal. But that password's only valid on that one particular computer there. So it won't help you go ahead and actually move laterally. But if someone tries to go ahead and authenticate against the Active Directory account, it'll send out an alert. So that way you can kind of start detecting some of this lateral movement that's going on in your network if someone goes ahead and tries to pass the hash with the wrong hash. So that's a really kind of cool tool. But part of that is you have to be able to make a password that fools an attacker so that they think it's actually a real account versus something that's set up to fool them. Because they're going to see that client tool on the computer as well that's inserting those passwords. Other usefulness for that there, if you're setting up a huge honeypot. I mean, if you want to create a fake Active Directory account or a server for people to break into, you don't want to have to go ahead and hand jam 1,000 passwords into it. So this is just a really quick way to be able to go ahead and generate those passwords and have those look fairly legitimate. Also, if you're going ahead and running a password cracking competition, if you need to create a large data set that looks somewhat real, this is probably one way to do it. So that way you can go ahead and you can run it, and these passwords are going to look a lot like the passwords that you trained on. I didn't put this in the bullet points, but also if you want to go ahead and just mess with people, you could create fake password data dumps too if you wanted to. So, I mean, they're just a lot of just kind of fun things. So this is one of those things that when I started playing with it, I was like, yeah, it's not really worth that much, but it's really easy to implement, so why not? And the more I've been playing with it, the more fun I've been having with it. Included in the tool set there is a tool to go ahead and generate honeywords from whatever grammar that you create. So you basically just tell it which grammar you want that you trained on, tell it how many passwords you want it to generate, and it'll go ahead and just go through that there. And that's actually pretty fast to be able to do too. So you can generate as many passwords as you want. So the other thing is with password policies. So as I mentioned earlier, if we can go ahead and assign a probability to a password, we can then go ahead and say, okay, your password is too probable. Where this is really nice though is, as I said, you can recommend passwords that are very similar to the password that the person created, but have just maybe one or two transitions that are different from how they selected it that would lower the probability of their password. So that way they can create a password that's kind of like the way that they want to, but it's a little bit more secure. Now, how you recommend these transitions has to be randomized too, because you don't want everyone who chooses the same password to automatically choose the same replacement. But you can start to go ahead and do this in order to kind of stretch out that search space an attacker would have to do in order to be able to crack them, while at the same time hopefully not infuriating users that much. And kind of going back to that keynote speak, you can start teaching people what makes a secure password and what's not by showing them examples of this here. So that when you show password 83 versus kitten 83 and saying are these passwords the same probability, people will be okay, kitten 83 might be a little bit lower probability password. That being said, about 1 week before I presented here, Carnegie Mellon University came out with this amazing paper, absolutely amazing, talking about going ahead and modeling passwords with neural networks. And the one nice thing about them is that the resulting neural network that they can send out is really small, so that way you can go ahead and incorporate it in let's say a browser. So I would say that if you're really interested in making more secure password policies, to go ahead and check out their work as well. They're going to be presenting this at, I think, SOUPS in a couple of weeks. Or Usenix, okay, sorry, yep. So that would probably be a better way if you want to go ahead and create better password models for password policies. That being said, after my depression came off and I had a chance to really read through that paper a couple times and realize that
what are you doing here?
Yeah, I know exactly. That was exactly what I was thinking. I had a chance to kind of look at this, and there are pluses to using probabilistic context-free grammars. And probably the best one is that I can go ahead and I can incorporate their work directly into my grammar. I mean, there's a Star Trek convention going on right now, so I can be like the Borg essentially. I can go ahead and take their techniques, and just like with Markov models, I can go ahead and incorporate their techniques in order to basically generate better strings. So actually this makes me very excited. So unless they can show that their entire model is better than using probabilistic context-free grammars at all, it's something that I can basically make my tools better. So what you're probably all interested in really though is cracking passwords with probabilistic context-free grammars. So really the first thing I have to say though, and this is going to probably be disappointing to everybody, is that the current implementation is god-awful slow. Okay, so when I run it, it's generally generated about 50,000 to 100,000 guesses a second. Now that may seem like a lot, unless you're used to using your hashcat cluster where you're making billions of guesses a second. So if you're talking about attacking a fast hash, don't use this. Okay, you're much better off using even pure brute force or something like that. Because you're just making so many more guesses that even the increase in the precision just isn't worth it. Where this is useful, though, is when you're dealing with hashes that are really slow. So let's say you have a large list of salted hashes, or you're trying to attack like full hard drive encryption, or doing something where the slowness of the guess generation it doesn't really impact your hashing of it because the hashing just takes so much time. So there's definitely still uses for this here. The performance of this is very dependent upon the grammar. I won't go into that too much here, but basically, depending on how many replacements you have and how many values can map to a certain probability in those replacements, it generates essentially very fine-grained word mangling rules. So the less fine-grained that you make it, the less overhead that you have in trying to generate in probability order, and then the faster the whole thing runs. And if you're interested about that, I can talk to you more about that later. So long story short, though, you can totally crack passwords with this right now, but it really is kind of geared more as a kind of a research tool. But that being said, probabilistic context-free grammars don't have to be slow. I mentioned earlier, Prince is really just a probabilistic context-free grammar. It's just a very specialized one. And I don't think anyone said that anything that Adam has ever written has been slow, okay? So, I mean, you definitely can take a grammar and move it back and then make it much more fast if you want to. Also, when talking about replacing, or how to make these grammars and stuff like that, you don't really have to make things really that fine-grained. So there's this really fun law called Zipf's law. I just love it because of the name. But it basically says that the probability of a word is, proportional to where it is. And what that means is like the most probable word is used a whole lot. The second most probable word is used a little bit less. But then you start getting down to this tail end here where all the probabilities of the different words kind of look pretty much the same. And if we just go ahead and flip this around here, this looks like just about every single password cracking session ever. And so the question was whether Zipf's law, applies to passwords. And there actually has been a paper that does that. And it says, yes, passwords follow this type of distribution here. Which is kind of, we should all know, password 123 is really common. Zebra 123, not so much. And what this means is that modeling the probability of these first ones here is really important. But after that, you can just be like, screw it, everything's about the same probability. And this is a way that you can go ahead and make the grammar a little bit more effective, or at least a little bit more scale a bit better with performance. Also, Carnegie Mellon University, they've been definitely doing their own work on password probabilistic context-free grammars as well. And their approach was to, in order to reduce the overhead, was to go ahead and spend all the time, generate all of these basically rules here, and then save them on disk and sort them, and then it's already there. So that way, all that overhead just goes away, and they can go ahead and make guesses with that at a much faster speed. So, it's not like we're using those disks for rainbow tables anymore, so we might as well be using them for something. So that way we can go ahead and start using these pre-computation attacks as well. The problem with that is when you do something like this is that you lose the ability to dynamically change your grammar after the fact. So if you want to go ahead and model it towards, let's say, a particular target, this pre-computation attack is not going to work quite as well. So kind of the deal with this here, I'm starting to look into maybe moving the grammar into the GPU. So the current PCFG cracker that I have right now, it tries to generate all the guesses in probability order. So it'll generate the first one, then the second one, and then the third one. In the GPU, you really don't care. You just want to go ahead and generate all the guesses that fall within a certain probability threshold. So that way you can go ahead and parallelize it. So what I can do is, I'm starting to modify Hashcat. Hashcat's open source, which I'm really psyched about. Version 3.0 is really cool too. And I'm basically kind of copying some of the techniques that Hashcat's already using in their Markov mode, where it uses what's kind of called it's a modified beam search, where you basically look at the different replacements and only do the first couple of replacements that you specify, and everything else you just kind of skip. And this way, you don't actually have to do any math whatsoever in the GPU, which is really big. And it also reduces the size of the grammar because any single replacement that falls below that threshold, you just don't even need to load up into the GPU at all. So basically, we're trading precision for recall. We're trading the ability to make guesses in probability order for the ability to make guesses massively parallelized. Now, I'm only in the very starting stages of this. I've forked Hashcat. I've been basically breaking it left and right. It's going to be a long time before I actually get this working, but this is definitely something that I think is going to be coming down the road here. If not by me, then by somebody else who can actually program well. So just kind of as my closing thoughts, just to show you kind of the differences in grammars. From last year here, I ran my previous grammar. I trained it on RockU, and I was targeting it on phpbb.com. This is Johnny Ripper's incremental mode, which is kind of a Markov-based attack. This is a previous probabilistic context-free grammar, and here's the currently one that we have released here. So, it's getting a little bit better here. It's only 1 million guesses. But still, for 1 million guesses, all of a sudden, we're cracking, 35% of the passwords in this data set that's completely different from the data set that we trained upon here. So when we talk about things like salted hashes, or it really helps to crack a lot of them really quickly, because that way it reduces your workload for making future guesses. This is something that's kind of nice just to run really first off before you start moving into your more traditional attacks. Now, when we expand this out to, let's say, 50 million guesses, you notice it really kind of hits this plateau. And as I said, that's kind of because of the limits of the dictionary itself, where the words just aren't really matching up with, say, the uncracked passwords that we're seeing here. So I'm hoping once I integrate Markov modes that we can start getting this, look more like a Zipf's law type of a distribution. Because right now it's just kind of hitting kind of a wall. But that being said, when you look at the difference in the probability, or in difference in how long it takes for the previous method to catch up to it, right here, it's about 1/40th the time in order to crack the same number of passwords. So this is where I'm really big about making the grammar itself be more precise, because even though it's not as fast or you're not getting those speed bonuses, you're reducing the cracking session time you have to run because you just have to make less guesses. So that's about it. If you have any questions, feel free to contact me on Twitter. I have a tendency to use like IRC. I really apologize. I'll just like post like 20 things. Or if you have questions, feel free to ask them now.
Questions?
Okay, just a couple of quick points. I don't think that your context-sensitive non-terminal is a cheat, or that it should be called context-sensitive.
Oh, if someone's saying I'm not cheating, I'm happy with that.
Yeah. I also think that when you're talking about Zipf's law with password distribution, I assume you're talking about David Malone's research.
Yep.
If my understanding of that, and also my look at the Adobe stuff, is that what he was saying is that this stuff superficially looks like Zipf's law, but when you do a proper statistical analysis, it isn't.
It has a tendency to break down at the tail there, but when you look at the front portion of it, it actually does follow it pretty well. So,
Matt, I've been using your tool for about 8 years now, so it's pretty great. Years and years and years back, there was really no memory limit. And so the limit on time was how much memory you had because it didn't really free up memory. So are you running in sort of somewhat reasonable constant memory now, or is memory still or space still a problem?
Memory is still a problem. So in the previous version, I'd kind of capped it out where it would basically free up that memory. And one thing that I'm really kind of struggling with now with the generic context-free grammar is it's hard to make use of those optimizations. What I'm doing in order to try to free up that memory is I'm just kind of dropping some very low probability transitions on the floor, so that when you're running this, it'll run in a constant memory space, but it'll eventually terminate much faster than what the grammar would do. So you're not going to be able to run across the entire grammar.
So you can't run for infinite time or constant memory?
Yeah, you can't run at infinite time with constant memory. Now, if you want to do it not in probability order, where you do something like a beam search or something like that, you can start going back through that the data set and run it in constant memory, though. But you're not going to have it in probability order.
Last one.
So I asked a variation on this question during the Wordsmith talk at 10 a.m. That is, when you generate a grammar and generate the probability table for each individual word, have there been attempts to expose that publicly, which is to say, given n+1 password leaks, can I check to see what the probability is for password I love you, 123, etc.?
So are you saying that, have I tested to see whether, when I run it against another data set, whether those probabilities match up with the probabilities I saw on previous data sets?
Yes, but also if that data is public in any capacity, because I've been looking for that.
So the short answer is no, as far as it being public, because people haven't been posting their grammars, and I'm included in that. So I mean, the fact that we're kind of breaking this up into all these different, like, here's the probability of these words, and you can compare that against different data sets. It makes it much easier to do. The one thing to be a little wary about is if you do post your grammars, it leaks an absolute ton of data about your training set, kind of by design. So you have to be a little bit careful because let's say you train it on some corporate passwords and then you post it online. Someone can really use that to figure out a whole lot about what your users are doing. So you have to be a little bit careful about that.
Okay, so we got to stop there to move on to the next talk, but thank you again, Matt. And you will, I'm pretty sure you will stay around as well. So, if anybody else would like to talk to him, feel free to do that. And we just have a very quick change here and we start again in, 6 minutes.